Today's lesson's notes can be found by looking at the Moodle, and you see where it says Notes for Video Lesson 6.6 and 6.7. That's the document that I'm going to be referencing. If you would like to, you can print that out or just view it online. Otherwise, you're going to have to copy it down. So let's go to that document. And you can see that today what we're trying to accomplish is to be able to visualize the four orbital types. What do they look like? How many of them are there? We also want to be able to define key terms. We'd like to also be able to understand how electrons behave within an atom. The big picture is that we want to understand that the quantum mechanical theory allows us to model what happens in light emissions. Remember, when light emissions occur, energy is given off, and those energies are clues to us as to what the electronic structure of an atom is. Where are the electrons? So quantum mechanical theory is a model that fits the data that we get from that light emissions. So let's take a look at this image. This is a picture of the four different orbital shapes that we're going to be discussing. And first one at the top, you can see they're color-coded. Of course, they're not truly colored, but an s orbital, which is spherical. There's only one of those per energy level. Then we have three p orbitals per energy level, each one on a different plane, x, y, and z. There are 5 d orbitals, and there are 7 of the f orbitals. Take a moment, sketch a picture of at least one of each of these so that you have a basic image and understanding of what they look like. Moving back to the document, you can see that we have a summary table set up that describes some different values related to orbital shapes. Take a moment and write it down if you haven't already printed it off. Okay, let's look at this table to give it to identify some patterns and some meanings. And I'll start by asking you a question. Which one of the columns indicates that there's a similarity between different shapes of orbitals? Okay, if you said that the fourth column is the one that indicates a similarity, you're correct. Notice that no matter what the shape is, one orbital can hold a maximum of 2 electrons. Next question. Can all orbital shapes exist in any energy level? The answer to that is no. If you look at the last column, the 6th column, you'll see the first energy level at which an orbital shape can exist. So the s orbitals can exist at any energy level, p can only exist from the 2nd energy level and further out, the d from the 3rd, and f from the 4th. Last question. What relationships, what trends do we see between electrons and orbitals? And that's not a very well-worded shape. Let me just explain what I'm trying to get at. Well-worded question. Notice that the s orbital, there's only one possible orbital of that type. For any p orbital on an energy level, there's 3 orbitals. For d, there are 5. For f, there are 7. And notice how many electrons that they can hold. The s orbital in total can hold 2 electrons. The 3 p orbitals each can hold 2, so that's a total of 6. Notice we're multiplying by 2. The d orbitals can hold a total of 10, and the 7f orbitals can hold a total of 14. Those are all important relationships that we are going to need to be familiar with. Take a look at the vocabulary. If you haven't written this down, if you haven't printed it off, do that. And we're going to talk about a video that we looked at last week, and we'll try to use some of these terms. Others we'll see later on in other lessons. I'll give you a moment to look at that, so pause it. Okay, hopefully this video looks familiar to you. You looked at it last week, and I'm going to use some of the vocabulary that we've listed on the Word document. And as we're going through it, if you hear a word, you don't quite understand how I'm using it, pause and take a look at the definition. If you're still not understanding it, write a question that you can ask in class. Okay, so what this is going to do, this video is representing the electron structure of an atom, and where do the electrons go. Notice that we have an XYZ plane, and at the origin would be where the nucleus is that has the protons and neutrons. Off to the side, what we're going to see is kind of a fly-in representation of these orbitals. Now understand, these orbitals really aren't flying in, they're always there, potentially for electrons to exist. So the fly-in is just for the sake of making it easier for you to see. Okay, so here we go. Now one thing I'd like you to notice is that at the upper left-hand corner of the screen we have the sublevel. So look up sublevel. The sublevel is the combination of the energy level, which in this case is the first energy level, which is closest to the nucleus, and the shape, which in this case is S or spherical. So the sublevel is 1s, energy level and shape. How far away from the nucleus, and what shape is it? Each orbital, represented by this round red ball, can hold a maximum of 2 electrons. Continuing our video, the next 2 electrons would go into the 2s orbital, which is further away, but it's also the same shape. Now we get into p orbitals. These are all in the second energy level, and each of these dumbbell shapes can hold a maximum of 2 electrons. One feature that I'd like you to note is that the p orbitals have lobes. So there are 2 lobes on this p orbital, and there were 2 lobes on the first p orbital. And again, each orbital that you're seeing fly in holds 2 electrons maximum. There's the 2pz orbital flying in. Any of these little spaces that you see that are unoccupied, where electrons cannot exist, are called nodes. One of the simplest nodes to understand is the one surrounding the nucleus. Electrons cannot go into the nucleus. But these nodes, these spaces that are available, later on get filled by more complex shapes. So now we're into the 3s sublevel. Electrons are going to be added from the simplest shape and the simplest energy level on up, and in this order that you're seeing right now. And we call that the off-bow principle. So it's just like if you're going to build a skyscraper, you wouldn't start by building the 3rd floor. You would need to build the base and the 1st floor and the 2nd and build your way out. Electrons do the same thing around an atom. You get the simplest shape first, being occupied, the lowest energy, and each orbital that gets filled is the next lowest one in energy. The other terms that we've mentioned here, Hund's rule and Pauli exclusion principle, we're going to talk more in later videos, but I can tell you that basically electrons are going to fill in an empty orbital of the same energy before they start pairing up. It's always preferred to go find your own space because electrons will repel each other if they have to share space. So that's Hund's rule, and the Pauli exclusion principle just defines how many electrons we can put in each one of these subshells, each one of these orbitals. You can put 2 electrons in each orbital, though a subshell might have several orbitals and might hold more electrons. Just a quick recap now. The things that we need to know. Closer an energy level is to the nucleus, the less energy electrons need to exist there. The simpler the orbital shape, the less energy an electron has to have to be there. Electrons fill sublevels from lowest energy requirement to highest energy requirement. Electrons also spin like a top, either clockwise or counterclockwise. When orbitals have to share a space, they will spin opposite each other. When they're in orbitals that are similar, they will spin the same way, which we would refer to as parallel. And in the next video, you're going to see that periodic table can be used to predict where electrons go. And so we'll be setting that up. So for the next video, you need a clean periodic table, 4 colors, whether it's marker, pen, crayon, whatever. And then you'll also need something to write with. And that concludes this video.